So the last two categories that we have to talk about, other than there's just categories that's like other, doesn't fit into any of these. But the last two real categories are the neuropeptides and the endocannabinoids. And then I'll sort of teach you why the things are named the way that they're named. The neuropeptides are a really, really clinically important group. So let me show you what they look like, and then we'll describe like how they're relevant to things clinically. So what we're used to up until now is that neurotransmitters are around this size, right? They're like about an amino acid size, even if they're slightly, different in shape, but they're about that size, right? You could count all of the atoms in them relatively readily. But here is one of the neuropeptides called, balls, where did it go? On the recording, of course. You wonder why I don't teach high school. That would be why. Hold on just a second. Oh, I had one more thing to show you, actually. Hold on. I do have high school students in my anatomy class, but they agree by coming to take a college class that they have to deal with it. And they actually love me. I'll show you that. Lots of people. You can read my reviews. Okay. So I want to show you the size of a neuropeptide. This one's called beta endorphin. I'll show you another one. How did I endorphin? Just so you can see their relative sizes. So these are the biggest ones. Oh, here's one. Here's a good one. Look how big that honker is, comparatively speaking. So what do you think about its rate of diffusion through the synaptic cleft? It's going to be way slower. These are not your super speedy, like alertness and responsiveness and like muscle contraction and skeletal muscle ones. So these are called the neuropeptides, and what they are is between 5 and 40 amino acids long, connected by peptide bonds. Okay, they're almost big enough to be considered a classical protein. They don't tend to have a whole lot of like secondary or tertiary or quaternary structure or anything, but they're way, way bigger than the other ones that we were looking at. And so I want to talk about their significance. So the neuropeptides are larger and slower acting, and they include a category of chemicals called the endogenous. But I need to teach you what endogenous means because it's a word you want to get used to. Endogenous means something that you make versus something that you take. So if I make a chemical, it's considered an endogenous opioid. If I get it from an opium plant, it's not considered endogenous. Does that make sense? So you have chemicals that you make, and then you have chemicals that are like agonists to those that you can take as drugs. So these are your natural opioids. These are the ones that you make. So I want to talk about the evolutionary significance of these, and then we'll talk about the drugs, of course, because the opioid epidemic is enormous in the United States. Well, as a whole, but in Utah it's huge. We're actually, last time I checked, we were 4th highest in opioid deaths even, and we have such a small population size compared to other states. We'll talk about why. There's a decent amount of data about why that is. Okay, so what do your opioids do for you? First off, there's 2 that you need to know by name, and they are endorphins and enkephalins. There's some others as well. What these chemicals do for you evolutionarily is I want you to think about what should occur in a situation in which you need to save your life or you need to lift something off of your baby regardless of the amount of pain that it causes you, right? So, what was the movie where the guy had to cut off his something hours, whatever. So how do you get through situations like that? Part of the reason you get through them is because in situations like that, you release these opioids, and opioids are natural reducers of pain perception. So it's not as if you don't know that the pain is occurring here. The sensory receptors are still being activated, and the pain is still being sent in. But in your brain, when you are flooded with these endogenous opioids, you don't perceive it as painful. Can you see how there would be an evolutionary advantage to that? right? Because pain is not worth your attention when you need to save your damn life, right? Right? Pain says stop doing that, but there's a bigger thing than stop doing that, right? If I need to lift a Volkswagen off my baby, for that moment, I shouldn't care if I rip every single muscle in my back, right? Okay? So in addition to being natural opiates and reducing pain perception, they also give you a high. They give you a feeling that your capacities are not quite as limited as they would otherwise be, right? You feel pretty damn good. And at the same time, evolutionarily, you should reward that behavior, right? Like, what should you do the next time your arm gets caught in a rock? Well, you got two arms. Let's try again. It worked the last time, right? Okay? So what they also do is they reinforce their own behavior with a combination of pain reduction, pleasure, and a dopamine spike. So they reinforce. Does that make sense? Okay. So you can see how they would be really useful. You also release them in other times, and other times it doesn't have to be as big an emergency. You are going to release some of these as a reinforcing chemical, for instance, when you exercise. I don't think mine work. I think mine are like, what is the opposite of an opioid when you're exercising? It's like, oh my God, is this over? You release them when you have sex. You release them when you like jump out of a plane if it's on purpose, right? You release them a lot of times. But evolutionarily, you can see how this advantage to reduce pain perception and also increase your perception of your own capacity. So now the problem comes in that these are the most effective analgesics that we've ever found. Analgesics are pain reducers, but of course they are highly, highly habit forming because they tap into the dopamine pathway. So let's talk about that. So the opioid receptors, first off, there are a bunch of different opioid receptors. Some are about pain and some are about pleasure and some are about perception and some will like reduce your breathing rate and those kinds of things. So you need to be as specific as possible as to which receptors you're dealing with. So there's delta, kappa, mu. The one that we know is related to dependence is mu1. And if you can block the effect at mu1, sometimes you can block the addiction sort of cycle. So I'll talk to you guys about drugs that they use to treat opioid addiction in just a second. So when opioids are released, dopamine is also released in this portion of the brain called the nucleus accumbens. And the nucleus accumbens is habit and reinforcement. By the way, every single time I wrote opioid in there, I just realized last night that I misspelled it. So let me spell it for you right. O-P-I-O-I-D-S. I always leave out one of the I's. So will you fix it, please? It drives me bonkers. It's probably been that way for 10 years, and I just noticed it last night. I'm like, what? Oh. Okay, so now, the drugs that we use to treat pain, a lot of times they are opioids. And so morphine, heroin, codeine, OxyContin, Lortab, all of those usually have some level of opioid or artificial opioid in them. And sometimes it's in combination with like a non-steroidal anti-inflammatory drug as well, right? Does that make sense? Okay, so these tend to be very, very effective at pain reduction, but the problem is that they are opioid agonists. What happens when you continually dump large amounts of an agonist onto a receptor? What happens to it? It downregulates, exactly. It downregulates, and then you don't get the same degree of either pain relief or pleasure from taking the same level of the drug. So then what do you do? Yes, you go try to find more, and when your doctor won't give you any more, you will go to a different doctor, and when that doesn't work, you'll try to buy them off the street, right? Because you need to remember that you're reinforcing this every single time that you take them, when you take them regularly. And then, fast forward, and you can't get any more OxyContin, and you can't figure out anywhere to buy them, and guess what? Heroin's cheaper, yeah? And so you can move on to street drugs. The problem is, of course, that these street drugs, of course, are even more massive about causing downregulation, right? In addition, these drugs can kill you because one of the functions is that they actually depress the central nervous system control of the respiratory system. And if you combine them with other depressants like alcohol, you can just stop breathing associated with these. So why are these such a big deal? So first off, sometimes we're just stupid about what we do. These have been around ever since opium poppies have been around for thousands of years, and we have been using them long before we knew anything about the physiology of how they behaved. And they are very, very effective analgesics. Morphine was a big problem in the United States. I think this was in the mid to late 1800s. And so they wanted to get people off of morphine, so they developed heroin to get people off of morphine. Whoopsie daisy! So heroin was created to get people off of morphine. And then OxyContin, there's a new formulation of OxyContin which makes it a little harder to abuse. That's one of the reasons they think that the rates of opioid addiction in Utah has fallen from first and second, which it was over 10 years, to about fourth, because we really like it in pill form here in Utah. And just so you know, without even trying to be edgy, they think that that is in large part because of the culture. Because we are in a culture in which alcohol has a lot of social stigma associated with it, as does any recreational drug. So you're not going to like snort it and you're not going to smoke it. But if it was prescribed to anybody in pill form, it doesn't get the same social stigma. But it still has the same predisposition for addiction. And so this is a big, big problem, sort of related to Mormon culture, because you don't think that you are actually abusing drugs when you take it because your back hurt or you got a toothache, right? And then you continue to take it because you actually get into habit formation. So this is a real problem here in Utah. And if you don't think that you know someone with an opioid addiction, I bet you're wrong. I bet you do know someone with an opioid addiction. So they're subject to downregulation of both pain response and pleasure. And then when you try to get off of them, the problem happens is if I get off for 6 months and then I have a really, really bad day, or I hurt myself again and I go back and I take the same drug that I was taking 6 months ago, how is it that I end up killing myself? Because you take too much. Because you took what you took 6 months ago, and then you were off 6 months and you upregulated your receptors again. And then you take so much that you actually kill yourself by depressing your respiratory system. So these are these major, highly habit-forming drugs that are subject to downregulation. So now, as we're all feeling very superior, I want to tell you that sugar addiction, which doesn't seem like it could be a thing unless you're a type 1 diabetic, and then it's a thing, right? Sugar addiction actually activates the same pathway in your brain as opioid addiction, and they can use some of the same drugs, like for instance methadone-related drugs, to treat sugar addiction. So we're all addicted to something, right? Yours might be oxygen, right? I can't go a day without it. Okay, but because people are interested, not because I usually test off of it, but maybe since I'm talking to you guys about it. So I want to just take a second and talk to you guys about the drugs that are typically used for opioid addiction or overdose treatments, because these are kind of a big deal. Have you guys seen all of the naloxone signs around? So now I think it just passed that cops carry naloxone and paramedics carry naloxone. So how does that work? Naloxone is an opioid antagonist, and what it does is it binds very, very tightly to the opioid receptors, and it doesn't let go. And if you do that when someone is in the midst of overdosing, you can stop the whole respiratory depression, and they might not die, right? They are going to feel really, really crappy, but they're not going to die. What about things like methadone? So if someone has an opioid addiction that is a long-standing opioid addiction, a lot of times what they try to do is they try to move them from that opioid to an opioid that's easier to maintain. Methadone is a long-acting opioid that has this analgesic effect, but it lasts for 24 hours and it doesn't really get you high, so you don't go into the seeking behavior. Again, usually it's given, you have to be like federally approved to be a methadone clinic. It's given as a liquid, usually, maybe some other way now. And you take it every 24 hours, right? And so this is kind of a maintenance medication. It's very, very difficult for a lot of people to get over an opioid addiction. So this is like, how do I have an opioid addiction and a life? And methadone is sometimes what people choose. And then this one, Suboxone. Have you guys heard of Suboxone? Suboxone is a drug that is a 4-to-1 opioid agonist to antagonist, but it's an antagonist at the mu1 receptor. So that mu1 receptor, that's the one for dependence. It gives you enough so that you get pain relief, but if you take an opioid when you are taking this one, you are going to throw your freaking guts up. So it's also got that sort of deterrent effect. So those are the three major ones that I thought you guys might be interested in, just how they actually work. So those are your opioids. I'll tell you why they're called opioids in just a second. One last one that kind of fits under the neuropeptides, I'm just putting it here because I think it might be important in the future. There's basically three different places that you could treat pain. You could treat pain at the sensation, you could treat pain at the perception, or you could treat pain during the pathway of getting in, right? What this one does is it treats pain at the sensation. It's called substance P. It doesn't actually tap into the dopamine or the reinforcement pathway, and it's in clinical trials to see if it'll be an effective analgesic in the future. So I just thought you guys might want to know about it in case somebody ends up developing something good about it.
That's the name of it, substance P?
Yeah, that's all what they're calling it right now. I don't even know what the P stands for. Okay, and then we'll switch to our last category, our last separate category, which are the endocannabinoids. And endo meaning you make them. And cannabinoid means that they have something to do with weed, right? Cannabis. Okay. So fascinatingly, people have been taking cannabis in one form or another for at least hundreds of years. I don't know whether it's thousands. And we only discovered the neurotransmitter and receptor system that it dealt with in 1992, which I know some of you guys are really young, but to me that feels like yesterday. 1992, like as long as we have actually been dealing with marijuana. So they discovered the receptor system in 1992. This is the neurotransmitter that actually acts on your brain. It's called anandamide. It's from the Greek word ananda, which means bliss. Sanskrit word ananda, that means bliss. And so what does it do? It works in the CNS and the PNS, and it's involved in pain signaling. So here was pain sensation, here's pain perception, signaling is going in, right? It actually works there in the pain signaling. And it works in the CNS and the PNS. Also works on working memory. It's crap on working memory, which means like you go into the kitchen and you can't remember why you went there, but like I live my life that way every day. No weed involved. Like why the hell am I here? I don't know. It's also involved in eating and sleeping patterns. For that reason, it has been used to treat anorexia before. It can actually give you an appetite and instigate your eating and sleeping patterns. It's also involved in pleasure and food rewarding. So the receptors for anandamide are called cannabinoid receptors, CB1 and CB2. And strangely, even though it took us forever to find them, they seem to be damn near ubiquitous in the central nervous system. They're just almost everywhere. There are these cannabinoid receptors almost everywhere. They're also present elsewhere in the body. So what does THC have to do with this story? THC and anandamide are very similar in shape when they actually fold. So here's THC and here's your anandamide. So THC from marijuana is actually a weak anandamide agonist. It doesn't fit very well, but there's so many receptors that it doesn't matter. So it binds to the receptors for anandamide, and it's an agonist. And so it gives you this reduction in pain signaling, crappy memory when you're on it, increased appetite, increased pleasure, and increased food rewarding. And one of the important things as far as using it as actually a pain reliever is that it does not tap into the dopamine reward system at all. So can people get into the habit of using weed? Absolutely. Can they actually tap into the dopamine pathway and become chemically addicted in the same way that you are with opioids? No. And will it kill you? No. It will not kill you. You cannot kill yourself. You can feel like you're going to die, but you cannot kill yourself. And so, of course, many, many states, not just California and Washington and all of the coastal states, but many, many states have legalized this for medical use, right? And so we in Utah are still using opioids just rampantly. If you were using it for instance, chronic pain, think about grandma, right? Grandma's in chronic pain because she's got rheumatoid arthritis, right? And we can give her opioids, realizing that opioids will, when used correctly, cause dependence, right? And can increase her likelihood of respiratory arrest, right? Or you could give her pot brownie, right? And it's grandma, right? So grandma probably likes brownies anyway. So we're probably going to have this debate again in Utah. The first time they had it in Utah, seriously, was about 5 years ago, and it didn't go anywhere. And then a bunch of Mormon moms said, we want the oil because it also reduces epileptic seizures. And then the oil got passed, but they did this weird thing where they said you can have the oil, but you can't buy it in Utah, and it's illegal to get it across state lines. So I don't know how they think that they're getting it, but that's the rule right now. And then the next step was that they said you can take it in pill form. So there is a cannabinol, there's a pill form. But the problem is the pill form has to go through your digestive system, and you have to up the level about 400% for it to cause a response in 30 minutes. Instead of anandamide, which is lipid soluble, and as soon as you take it in, if you took it in aerosolized, you can feel it within 30 seconds. You can get pain relief within 30 seconds. So last year they had another debate in the legislative session, and it came to as close as it has ever come to passing in Utah. Just medical. They weren't even talking about recreational marijuana. But unless someone comes up with a better option to opioids, this one seems like a far less severe option, especially for chronic pain. Go ahead.
So why do they give you codeine when you have pneumonia or bronchitis?
Oh, interestingly, codeine, one side effect of codeine, and not all of the other ones, is it actually relaxes your bronchioles. Yeah, and it can really be good for coughing. As a matter of fact, that's how half the people who got addicted in the 1800s, it was because through tuberculosis and consumption, they were taking opioids that actually allowed them to not cough their guts up. So anyway, what?
Morphine does the same thing, right?
Yeah, morphine does the same thing too. So yeah, there's morphine, there's cough syrup with morphine in it and that kind of stuff. So anyway, you guys can be involved in the next debate that we have about legalizing medical marijuana here in Utah. I vote all the time, but I don't think my box is hooked up to anything. Do you? In Utah? I don't think it is, right? It's fine. I'm just going to do it. It makes me feel better. Okay, so the other thing, here's a little one. Anandamide, there are clinical trials because anandamide itself, not THC, but anandamide, actually inhibits the growth of breast cancer cells. And so they are seeing whether anandamide or THC can actually work. This is still in vitro, not in people. And then one of the reasons you like chocolate, if you like chocolate, is because it feels a lot like weed. Just so you know. Especially if it's really, really high cocoa content, like super, super dark chocolate. Weak anandamide agonists are also found in cocoa and chocolate, and it can give you that little pleasure that goes through your brain. It's also lipid soluble. So anyway, this one's the endocannabinoids. There will be more discussion about those in your life, I'm quite certain. Okay, miscellaneous neurotransmitters. These don't fit into any of the other categories, but I think it's kind of interesting that they are neurotransmitters. Nitric oxide gas, not nitrous like the giggle gas from the dentist, but nitric oxide gas is actually released as a neurotransmitter. And the reason we know so much about this one is because this one is the one that's involved in erectile dysfunction. And if you want somebody to give you a whole bunch of money, you make a rich man's wiener not work. And then you get some money. So yeah, there is a whole bunch of research money into nitric oxide gas. They're like, do you want all of my money or half of my money? And then another one is interesting. Carbon monoxide, if you breathe it in, it will kill you dead as a hammer, but your brain actually makes it and releases it as a neurotransmitter, which confuses the hell out of me. I'm not quite sure. We don't even know what it does up there yet, but they found it just a few years ago. Okay. So, receptor functions. Okay, so why the heck are things named oids and ergics and all of that business? It's because a lot of the time what you're seeing is the history of how this thing was found. So, it should make sense to you that a lot of times people have been doing drugs that mess with the neurotransmitter system long before the neurotransmitter or the receptor was found, right? So, often the impact of a drug is known long before the receptor or the endogenous chemical. People used opium for thousands of years before opioid receptors or endorphins were understood. As a matter of fact, the opioid crisis was so huge in China during the opium den era that they could not stop people from doing opioids because it's actually a chemical addiction in your brain, that their solution was that anybody who did opioids and got caught had the death penalty. So they took care of their addiction problem by killing most of their addicts. It was the death penalty was the actual result of that one in China. Yeah, where opium grows really, really readily. But does it make conceptual sense to you that the receptor and, of course, the neurotransmitter had to predate the drug? It's not like I have opium receptors. It's like I have receptors that bond to something that I use, right, and also bond to opium, right? Okay, meaning that there are no opium receptors in the brain. There are receptors that bind to an endogenous chemical and also bind to opium. The drug can give rise to the receptor. However, if you found the drug first, that's why we call them opioid receptors or cannabinoid receptors, right? Or you could have found the chemical before you started messing with it. Like GABA, we found, called the receptors for it GABAergic. And then the drugs that interact with it, like the benzodiazepines, interact with GABA receptors. So the problem is, of course, that it's not super consistent. And the reason it's not consistent is because the historical nature of discovering the things wasn't consistent. Okay, so you guys got the idea? Okay, so what we're going to do now, you're not going to like it. Nobody ever likes it. I don't even like teaching it, but we're going to do it anyway. Now what we're going to talk about, we're done with the neurotransmitters. Now what we're going to talk about is the types of receptors that exist, okay, just generally. And these are receptors for all chemical messengers, some neurotransmitters, paraffin agents, hormones, that kind of stuff. So, and then we're going to talk about how in the target cell you will cause a response. So stick with me for a second. I want to be a chemical messenger, and I want Sabrina to be the receptor. And I want you guys to all be the cell organelles, okay? And so what's going to happen is if you guys at the back are the nucleus, and what I want to do is force protein synthesis. I bind to the receptor, but if I'm water soluble, I don't get to go inside the cell, right? Okay, so I bind to the receptor, so I have to make the cell play telephone. Yes? So you're stuck there. You have to tell her something. You have to tell her something. You have to tell him until we get it all the way back to the nucleus, right? So it's like playing telephone. Yes? Okay? And so this telephone is called a signal transduction pathway. I'm a signal, yes, but I can't go inside, so it has to be transduced, and there's a pathway by which it occurs. It can either be a really long game of telephone if I have to stay outside, or what if I instead was lipid soluble? Couldn't I go straight to the nucleus and tell it myself? That's the shortest game of telephone, right? Either way, it's a signal transduction pathway. It is the way that you get the target cell to do something. Yeah? Okay. So, there's two categories of signal transduction pathways. We have the ones that are initiated by intracellular receptors, and we have the ones that are initiated by extracellular receptors, or cell membrane receptors. So you guys tell me, intracellular receptors will be for blank soluble chemical messengers, lipid. Cell membrane receptors will be for blank soluble chemical messengers. Water, exactly. Okay, so let's do the easy one first. The shortest game of telephone you can play is with a lipid-soluble chemical messenger that goes straight inside the cell, yes?
Yes.
Okay, so this signal transduction pathway is initiated by an intracellular receptor. So what I'm going to do, I'll show you an image and then I'll show you an animation of it. So here's my lipophilic or lipid-soluble chemical messenger. It's going to diffuse straight through the cell membrane and find its receptor either in the cytoplasm or in the nucleus. And then what it's going to do is it's going to go straight to the gene for the protein that it wants to cause synthesis of. It's going to bind to it and force transcription, yes, and then translation. And that new protein now is something that I didn't have before. What is it? I don't know. It could be an enzyme that I didn't have before and now can function. It could be a protein that's meant for exocytosis. It could be a structural protein that changes something structurally about the cell, but it didn't have it before. Does that make sense? Okay, so this mechanism, I'm about to show you an animation of it. This mechanism is called gene activation. Does that make sense? And it's the shortest game of telephone, and it's only for lipid-soluble chemical messengers. So let me show you an animation of that one. I lost it. Just hold on a second. Okay. Okay. So we won't listen to them. I don't want to listen to them. So this is using, oh wait, not that one. Sorry, that's the wrong one. This one. I'm sick today, so I am dumb, and you are seeing dumb Melanie. Okay. So, aldosterone, it happens to be a hormone, doesn't really matter. Travels straight through the plasma membrane, finds its receptor inside the cell, and it can go straight through the pores of the nucleus, and it is going to go to the specific region of DNA that it wants to cause transcription of, and it will cause transcription. And then that has to leave to do translation, right? It has to go back out to the ribosome. And I will do translation. And this protein that I have now means that the cell can behave differently, either structurally or functionally, right? It can either be shaped differently, have some different conformation, but exists now, and now the cell can be different, right? That makes sense? So this is gene activation, and it is only for lipid-soluble chemical messengers. So we will see when we get to the endocrine system that there's an entire category of chemical messengers called steroids that use this mechanism. Okay, so now the plasma membrane receptors, the cell membrane receptors, those are going to be, again, you told me before, but tell me again, for blank soluble chemical messengers, water soluble chemical messengers. There's going to be 4 categories of them. Okay, so the first one you've already met, you just didn't think of it in this context particularly before, and that is a receptor, a cell membrane receptor that is also an ion channel. Have you not met those before? Yes? Chemical gated ion channels, right? It's a receptor that is also an ion channel. So let's look at how those work. Here's a chemical messenger. The ion channel was closed. Chemical messenger binds. Now the ion channel is open. And that can either depolarize or hyperpolarize the cell if we wanted to. It could be that initiates muscle contraction. You could use that calcium entering to cause secretion like exocytosis, right? Or you could cause it to, for instance, change something long and complicated inside the cell. But it starts with opening an ion channel. So you have seen these before. You saw a whole bunch of sodium channels and some potassium channels, right? I will tell you that calcium channels are really common ways of making things happen inside the cell. And that a category of receptors that we've already talked about, the nicotinic cholinergic receptors, these are going to be, what do you think, faster or slower than causing gene activation of a protein? Faster, way faster. Now, you get there for gene activation very quickly, I agree with you, but protein synthesis is not very fast, right? But allowing an ion to go in could cause immediate exocytosis of a neurotransmitter, for instance. So these are really fast. So don't be at all surprised that you see them with those nicotinic cholinergic receptors that are responsible for like alertness, right? Or for learning, attention, memory. They're also the ones that actually stimulate skeletal muscle contraction. When you want skeletal muscle contraction to occur, do you want it to occur when you command it or like 30 seconds later? When you command it. It's your emergency response tissue, right? So these are pretty fast receptors, okay? Second type of receptor, a receptor that is also an enzyme. These are the second type of, okay, so stick with me, we're almost through. Okay, so look, this is one protein, this whole thing, green, purple, green is all one protein. This end of it behaves as a receptor. This end of it behaves as an enzyme. Okay, this receptor is also functioning as an enzyme on the other side. This is called a tyrosine kinase receptor. When the ligand binds to it, what it does is activates the enzyme. And who cares? What this enzyme does is it phosphorylates the tyrosine amino acid of another protein. And why do you care? Because that protein was inactive and then you just activated it. So I just turned something on in the cell by doing this, okay? So these are called tyrosine kinase receptors. They're very big. They're a very big group. They are very common for hormone receptors. Okay, next category. These your textbook for some reason did not have a picture of, so I'll show you a picture from a different textbook. These are very much like this one, so stick with me for a second. This one I had one protein that had an end that was a receptor and an end that was an enzyme. This one has two different proteins. One is a receptor, it is stuck to an enzyme. Okay? This is such an enormous group that they are the most abundant type of receptors that we've found, and they do something very similar. It's also a kinase. They phosphorylate something and therefore activate a protein in the cell. There are so many of these that they got named JAK kinases, which literally means just another kinase. Because they found so many of them that they got tired of people naming them after themselves. They're like, oh, you found a kinase in a cell. Did you also find hay in a barn? Because there's so many of these. So these are super duper common. You're going to see them all over the damn place. Growth hormone and prolactin, these are JAK kinase receptors. And really the only difference between a JAK kinase and a tyrosine kinase is that tyrosine kinase, all one protein, JAK kinase, two proteins stuck to each other. Okay, so last thing is the most complicated one. And before we get to that, let me tell you why the hell I take a minute to talk to you guys about this. Because if you are going into nursing, for instance, or if you're going into pharmacy, do you think that you are going to spend a hell of a lot of time understanding what drugs interact with what specific receptors? So receptors end up being a large part of what you're supposed to understand. And this is the first time that you have been exposed to the categories of receptors for chemical messengers. So for instance, when you are reading a PDR, a physician's desk reference, or a nurse's reference, it will say that this drug acts as an antagonist for the JAK kinase receptor for this, right? And then at least you won't go, I have literally no idea what the hell you just said. You will say, I have the very smallest recollection that I've heard that word before, right? And it's better to have the smallest recollection that you've heard that word before. Okay, and then the second biggest group, I don't even understand how these evolved. They are the strangest things. It doesn't seem like they would work at all. These are the G protein coupled receptors. I've got an animation for this one too. So, with this picture, what I really want to do is I want to activate this protein. Let's say it's an ion channel. I want to open it, right? But instead of opening the damn ion channel, what I do is I use 4 other proteins to make it occur. It's like this is the pocket you want to shoot in, right? But instead of doing that, you're going to do a tricky 4-ball combo shot, right? Okay, so what's going to happen is the chemical messenger binds to another protein over there that changes the shape of this one and slides these 3 G proteins through the cell membrane until that one smashes into that one, and that's how you open it. I can't even believe that they work. It seems like something would go wrong every time you tried to do this. Have you ever tried to make a 4-ball combo shot? I've literally never made one on purpose, right? It's just on accident that I've made them. So these are called G protein receptors because they use GTP, guanosine triphosphate, as the energy source instead of ATP. Okay, so let me show you an animation to make it make a little bit more sense to you. Okay, you ready? So this water-soluble chemical messenger is going to bind here. Go faster. It's going to change the shape of that first protein, that receptor protein. And it's going to change the shape such that these 3 proteins slide through the cell membrane. And while it's sliding through, this alpha subunit right here is going to slide off and it's going to smash into that protein right there. And that's how you're going to open it. Okay? When this falls off, the whole thing is going to be attracted back as long as you have GTP to put it back into position. So that's going to fall off. It's going to be the right shape again. Everything's going to slide back. And you're going to be able to use it again. So does it seem strange to you that this thing evolved at all? In Texas, we would call this going around your ass to get to your elbow, which is like making things way harder than you need to. Have you ever heard that expression? He has? Oh, goodness. Good. I bet Nikki would have heard it. Nikki's from Kentucky. We always just redneck bond. We're like, oh yeah, yeah, sure. Okay, so just so you know, this right here does not have to be an ion channel. It could be an enzyme, and smashing into it is how you activate the enzyme. But either way, you use all 4 of these proteins to activate another protein. So why do you care? Because look how many. The muscarinic cholinergic receptors are G protein receptors. The alpha adrenergic and beta adrenergic receptors, including the ones you find on the heart, those are G protein receptors. And your serotonin receptors are also G protein receptors. So this is a pretty darn important group, especially for medications. Yeah? So if we use beta blockers, what they do is they block the effect of the G protein receptors, right, for epinephrine and norepinephrine. Okay, so to bring it back around, what happens at the end of all of this signal transduction? Why did you go through all of this? Because you wanted to change the activity of the cell. And how can you change it? You could like induce cell division, you could cause protein synthesis, you could cause apoptosis, you could depolarize or hyperpolarize, but that's how you get the cell to behave differently, is by these signal transduction mechanisms. Is that okay? Okay. All right, so the last thing in this set of notes, and then I will show you guys a study tool, is to talk about nerve impulses and how your body decides what to pay attention to versus not pay attention to, and what attention actually has to do with. So what we already know about nerve impulses, and you know almost all of this, if you want to get an action potential, you have to start out with a graded potential, right? You always do, right? You want to get an action potential, you have to start out with a local or a graded potential. And if it hits threshold, then you get an action potential. But there are no strong or weak action potentials, right? So what's the difference between a loud sound and a soft sound? What's the difference? It's frequency, yes. So you guys know that. Okay, so now I'm going to add a little bit to that. So the magnitude of whatever you're communicating in the nervous system is stimulated, is coded by frequency, and we already know that, right? But now what I'm going to tell you is that your nervous system is smart enough to know that some things are worth more action potentials than other things. So, and it's not just intensity. So what I want you to imagine is that your body has the capacity and your brain has the capacity to figure out whether a constant stimulus, you should worry about sending very frequent action potentials when the stimulus is constant. Like right now, you can feel your clothes on your body, but you are not sending very frequent action potentials because that's expensive, right? You can hear my voice, but you could also hear somebody wiggling around in their chair, and you can hear the air conditioner. And one of those you're actually sending more frequent action potentials for than the other. Sometimes even if they're at the same amplitude or the same loudness, right? You can actually sort of determine where you send it. So let's talk generally about how you do that. This concept is called adaptation or accommodation. And it means that when you're exposed to a constant stimulus, you reduce the frequency of action potentials and the sensitivity of the receptors. So what I want you to imagine is, let's go back to a proto-human walking across the African savannah 100,000 years ago, right? Somebody's walking across the African savannah. You've got all of these inputs coming in. You can hear the wind, you can hear the water, you can hear the birds, right? You can hear the grasses. And all of those are going in, and you're really not attending to them, right? But they're all going in, yes? It's not like you don't hear them. But then you hear very, very faint, a new sound. And it doesn't have to be loud, right? But it's novel, right? So you are set up so that every novel stimulus gets frequent action potentials so that you can assess it. Does that make sense to you? Okay, so you can assess it. And if it will kill you, if you can eat it, if you can have sex with it, you'll probably keep the action potentials really, really high, right? If it doesn't fit into any of those categories and the stimulus becomes constant, then the receptors are like, meh, and the frequency slows down, right? So I want you to think about it if you're a parent. I want you to think about studying in the other room, and your kids are playing in the other room. There's lots of kid noises going on in there. They're like annoyed at each other, and there's like some bleep bloop thing happening, and something's falling over, and somebody's pissed off at somebody. But it's all normal kid noise. And then you hear silence. What happens? What the? Right? It doesn't have to be loud. It just has to be different. Yes? So you are set up to notice changes and to assess the changes. And then you also have a certain predisposition, not as much as you think, to use your own cerebral cortex to decide what to attend to, right? So you can decide to attend to my voice because you paid to be here, right? Or you can decide not to, right? You don't have as much control over that as you think, though, because if somebody's clicking their pen next to you, can you actually decide not to listen to it? No, you can decide not to murder them. That's what you can do, right? Okay, so we are set up to notice changes. This is why, have you ever driven through a stinky town? Have you ever wondered how anybody can live in a town that smells like a foot? Right? What?
They get used to it.
Oh yeah, they just get used to it. That's what happens. It's a constant stimulus. In Texas, there are sawmills everywhere. And the sawmill towns smell like butt foot. It smells disgusting. And you walk and you drive through and you're like, how the hell could anybody live here? Well, do you think they can still smell a fart? Yeah, a fart is a novel sensation, right? Can they still smell perfume? Yes. But they just basically become less sensitive to the constant stimuli. And the last little bit is that males and females are different in our predisposition for adaptation and accommodation. It has to do with the fact that until about the last, 75 years or so, our roles were pretty carefully delineated, especially before the agricultural revolution. And so think back a ways, we tend to live in groups, but the women tend to stay back with the other women and the old people and more children than you can keep alive, right? Because someone's always trying to eat them or going to walk off something, right? So you're going to divide your focus. Women tend to be very good at multiple focus, comparatively speaking, yes? Men, on the other hand, tend to be predisposed to a series of single focus activities, right? You're going to go out, you're going to hunt the wildebeest, you're going to kill the wildebeest, you're going to drive the wildebeest back home, you're going to feed your family the wildebeest, you're going to have sex, you're going to sleep, you're going to go do the same damn thing over again the next day. So they tend to be very good about adapting out extraneous information. So when you are talking, right, and they are watching their wildebeest, which is football, I don't know what the hell, my husband's is computer programming or a video game, I think that he's listening to me and he's not listening to me, but it's not the same as if I wasn't listening to him, right? Because I can actually hear our conversation and eavesdrop simultaneously. Right? I can do all of that. Women tend to be on this side as far as the adaptation and accommodation. It's a little harder for them to adapt out extraneous information, and men tend to be on this side. Now, am I saying every man and every woman is like that? Absolutely not, right? It's a spectrum. But if you get 100,000 years of evolution causing you to diverge that way, you certainly see it more distinctly in males and females that way. Okay, so I always say you just need to be the wildebeest, right? If you want your man's attention, you got to be the wildebeest, right? You have to remember if he wants something that could kill him, right? Something that he could eat or have sex with, right? Any of the three. And you are just being the wind through the grasses. Okay, so I want to show you a resource. I've already shown it to you, but I want to show you how useful it is so that I can encourage you to use it. Okay, so we were talking about this in my office today, and I talked about it with a couple of other people. This is interactive physiology. So I want to show you why it's useful, because I know sometimes some of you who are very kinesthetic and need to be hands-on have a harder time with phys than with anatomy. And what I want to tell you is this is the place that you can be hands-on. So let me just show you a little bit. If we go to, first of all, if you look at your notes, open recent, I give you specific regions in which you can go look at interactive physiology. Nervous system 2, synaptic potentials and cellular integration. So you can go to there and nervous system 2, synaptic potentials and cellular integration. And that will allow you to practice. Sometimes I even tell you which specific pages to practice. But let me just show you what it will do and how you can practice. And then I will tell you that it actually gets pretty hard, so you're not going to get all the answers right all the time. Okay, so let me show you page 3, I think.
We have examined the anatomy of a synapse. Now let's look at the details of synaptic transmission. Click the presynaptic neuron to produce an action potential. An action potential in the axon terminal causes voltage-gated calcium channels to open and calcium to enter the terminal. Click the presynaptic neuron again to see the calcium channel in action.
It'll actually show you where calcium is going. And then the quizzes are hard. So with this one, what you have to do is you have to click everything in order that would occur for the synapse. So what if I click the voltage-gated calcium channels first? No, that can't happen first. I have to do an action potential first, right? And I'm like, oh, okay, that causes neurotransmitter release. No, not before you have your voltage-gated calcium channels, right? And then you'll get your neurotransmitter release. And then the neurotransmitter will be released, and then it's going to bind to the receptors, and then you'll have the reuptake mechanism. And then later on in the quiz, they'll let you chunk drugs into the synapse and watch what happens. So for those of you who are very kinesthetic and really like visual learners, this is a way to practice. The quizzes are really good, and the worksheets are kind of hard. They're good for review. So if you have a new textbook, it's in mastering. Right, it's a little subsection of mastering. If you don't, then I put a link on melanieb.com for you guys to the free one. It's a decent use of your time. You can see that you can actually mess stuff up, and then it will actually help you fix it. Okay.
We've examined the anatomy.
I just wanted to show you guys that. All right, so briefly, just with the last few minutes, we will, I'll just give you guys a brief intro to the muscle stuff that you're about to start doing. Okay, so you guys are doing muscle in lab this week. This is one of my favorite labs for phys. And so let me tell you a little bit about lab, and then tell you a little bit about lecture, and also clarify something so you don't get confused in lab. Okay, so what you guys are going to be doing in lab this week is you are going to artificially be using an electrical stimulus from outside to start muscle contraction. That would normally be happening with synaptic transmission, right? Yeah? Okay, so what was that look? Your lab look?
No.
Okay. Lab's getting better. I know it's not as good as anatomy lab, but that's because I'm the director of anatomy lab. Well, the whole last chapter that we just did was synapses, right? But we know that a neuron can synapse on a neuron, which is what the whole last chapter was, or a neuron can synapse on a muscle cell. Yes? Okay. So what you guys are going to be doing both in lab this week and also in this set of notes is you are going to be looking at synaptic transmission and how it leads to muscle contraction. Okay. So I want to point something out to you and see if I can clarify it before you get into lab so that you're not confused. Okay. Do you remember the concept of summation or temporal summation in muscle and neurons? Okay, what's happening on the presynaptic cell? Presynaptic cell with temporal summation. What's it doing?
More frequent.
More frequent action potentials trying to get the postsynaptic to threshold. Yes. Okay. Now you can do the same thing with the presynaptic cell on muscle. Only think about it for just a second. If I stimulate a muscle cell with a presynaptic neuron over and over again, what do you think I'm trying to make happen on the muscle cell? Any idea? Yeah, for it to twitch. If frequency coding works both ways, it's not just, for instance, more frequent in means louder sound, but more stimulation out. What can you tell me about more frequent stimulation on a neuron? What do you think it will do to the degree of muscle contraction? Cause more muscle contraction, exactly. So if you zap yourself more. So students get kind of confused because the word summation is used both in neurons and in muscles. But really the reason it's used the same is because the presynaptic cell is doing the same thing, isn't it? The presynaptic cell is just frequently stimulating the postsynaptic cell. Only with this one you're trying to get to an action potential, and with this one you're trying to get a stronger contraction. Okay, so you will see that. You will see that if you just zap it once, you might get a contraction, but what if you zapped it? You'll get that, right? Volunteer to be the zappy. It's fun. It's super fun. And you get to review some nerve stuff from anatomy as well. Does that make sense to you guys? So I don't want you to get confused when you get to the concepts of threshold and summation because they're similar, right? And that's why they have similar terminology. Okay, so we'll come back to that. The last thing that I want to tell you guys is that if your anatomy isn't really strong, you're going to need to go back and review it, because what I want to, when I see you guys on Monday, is I want to start with you guys understanding the basic structure of the sarcomere, right? Which was taught in anatomy. If you have trouble remembering that, you can of course look at your textbook. You can also look at interactive physiology. At the beginning of every section of interactive physiology, they have an anatomy review in which you can label things and figure all of that out. So you can use that as well. Make sure that is fresh, because that's the starting point, and then I'll teach you the real physiology, right? And so we'll have less time to learn the physiology if you don't actually brush off the anatomy. All right, so 2 things as you guys are just about to leave. Tell you a couple things about muscle that is important. First off, muscle is incredibly energetically expensive tissue, which means it needs a really, really good blood supply. So every single muscle cell that you have has a little snuggly nest of capillaries around it. And so it looks kind of like this. So this is skeletal muscle. This one was stained so that you could see the capillaries. This is why a cow muscle, cross-section of a cow muscle, is called a steak, right? When it sits out on your counter before you cook it, it is red because it is incredibly vascular tissue. Does that make sense? In addition, each cell will be red as well because it has some oxygen bound to stuff inside the cells. So it's going to be incredibly vascular tissue. And the other thing is that the tissue is highly, highly innervated. So each muscle cell, and that's one muscle cell, has to be told what to do every damn time by the nervous system. Okay? So I want you guys to imagine that these 4 are muscle cells. Okay? And if I only tell her what to do, then these 3 do absolutely nothing, absolutely no initiative whatsoever. So if I don't tell both of you and both of you every single time, you will not do anything. That means that if you ever cut that axon, that muscle cell is paralyzed and will never do anything. So if in the gluteus maximus you have 100,000 muscle cells and you cut the axons to some of them, you will have partial paralysis, right? That is unlike cardiac muscle. If I told her, with cardiac muscle, if I gave her a command, all of them would do it. Why? What do they have? Gap junctions, exactly. But, so they work as a team. But skeletal muscle is more like a teenager. So if I tell my 17-year-old to take out the garbage, but I do not tell him to put another bag in, is there any chance that he's going to put another bag? No, there is. Those moms are like, it is never going to happen. And how many times do I have to tell him to put another bag in?
17.
Yeah, exactly. Like, but if he took out the trash every day, would I have to tell him every day to put the bag in? Yes, every single time. That's a skeletal muscle cell. They will not do a damn thing unless they are told to every single time from the beginning with a complete set of instructions, right? And so, highly, highly innervated tissue. This is why, for instance, if I had nerve damage, if I damaged my radial nerve, which innervates the muscles on the lateral side, right? If I had nerve damage, I could end up with, for instance, muscle weakness. If I lost connection to a few and I couldn't, for instance, abduct my thumb or my pollicis very well, or I could end up with muscle paralysis and it just doesn't work at all if I cut all of them. Does that make sense? Okay, we'll stop there and I'll see you guys on Monday. It's weird to only see you once this week. Let me save this because I'll forget. Egg. How did I get another cold?